Thanks so much, everyone, for sticking around. We've had a really exciting day, I think. I'm Dominic. I'm a postdoc here, and I'll be moderating this panel. I guess I want this panel to be sort of a like getting a take from everyone on the panel on what like important open questions are in the field now. I guess we've heard a lot about theory advances. I feel like we've thought a lot about random circuits in the past few years. We've learned a lot about them being designs, pseudo-random unitaries. We've learned a lot about their hardness. We've also thought about verifiable advantage. And then on the other hand, we've had these great experiments where there have been demonstrations of quantum supremacy, as they call it. And I'd like to sort of focus the panel on the sort of open questions in theory world, but also the connections to, let's call them TCS experiments, like things that we want to run on a quantum computer because we think it's interesting just from a sort of theory perspective. Okay, and just to sort of go through our speakers or panelists again, we had Andrew this morning talking about verifiable advantage on like a NISQI setting, and then André on improving factoring algorithms in terms of the resource requirements, Sean on improving robustness in proofs of quantum advantage, and then Alex on maybe applications of random circuits to pseudo-random unitaries. And then I guess you all know Scott, who is here as...
I didn't speak about anything.
Right, but he will always have an opinion, so that's great. Awesome. So maybe I can start off with a question to the audience, actually. Maybe everyone can raise their hands who feels like or is like convinced that we've actually achieved quantum advantage in experiments. Oh, that's a very low.
Maybe ask who's convinced that we have.
Exactly.
Exactly, and who's convinced that we haven't? Oh, I guess most people are undecided. Oh, interesting. If you had to decide, which side would you pick?
Shouldn't we have the lecturers from Monday here because they're actually building real hardware?
Right. Yeah, we actually did want to have Dolev on stage, but he couldn't make it, unfortunately. So we'll simulate Dolev for now. Okay, so if you had to decide one of the two, who thinks quantum advantage has been achieved? Okay. And who thinks it hasn't been achieved? Okay, it's pretty even. Interesting.
I have a question.
Depends what you mean.
What if, does it count if we achieved it, but we haven't proved that we achieved it?
Right. Great. I think, the question was maybe intentionally vague. Sorry?
All the time.
Yeah.
It's like a religious question more than a scientific question.
I agree. Okay. Great. So I want to, in this panel, sort of go through three themes. The first is, open questions in theory. The second is connections to experiments. And then the third one is maybe an open-ended applications and sort of a zoom out, like what are the big important questions. Okay, and so maybe first question again, I want to just briefly go through the panelists. We've sort of heard about factoring and heard about random circuit sampling. If you had to bet on, one of the two getting broken, what would you bet, on factoring getting broken versus random circuit sampling? The hardness, yeah, classically broken. Let's just go through.
I mean, I think you need to clarify what it means to break random circuit sampling. Right?
Let's say there's an efficient algorithm to simulate random circuits.
No, but spoofing the linear cross entropy benchmark, breaking it with noise, those seem very plausible. Like a full break that samples the same probability distribution, that seems extremely implausible.
Okay.
Right, with factoring sandwiched somewhere in between those two.
Okay, great. That's an answer.
I'm very confident in factoring. But you could also say that the number of people who are actually trying to break factoring classically now is actually quite low, I think. Maybe there are even more people trying to do random degree sampling at the moment. So.
Yeah, I don't think I have an opinion on. I think both of them are hard. It's very hard for me to say which is more unlikely. Yeah, in some sense. So I've heard this argument that do you think that a collapse of the polynomial hierarchy is more likely than a polynomial time algorithm for factoring? And my first intuition is to say, well, I find collapsing the polynomial hierarchy to be more unlikely. But then people will say, well, but factoring has been studied far longer. So maybe, there's reason to believe that that's the harder assumption. But yeah, I've kind of gone back and forth on it, but I don't have a good opinion.
Okay. Alex, Sean? Sean has no opinion.
Yeah, I mean, what these hardness proofs say is that they should both be, I mean, is that random circuit sampling should be hard, right? I mean, there's not sort of an analogous sort of complexity. Our understanding of the complexity theory landscape is not that drastically affected if factoring is in P. But for other reasons, that would be a big surprise. Mm-hmm. So, I don't know, I would expect they're both hard. But that doesn't necessarily bear on the experiments, the random circuit sampling experiments.
Yeah. I think Alex has his own micro, so.
There's a lot of fancy number theory out there in the world, and I wouldn't say that I'm that convinced that we've understood why all the fancy number theory in the world can't give a polytime algorithm for factoring. Mm-hmm. Although, yeah, I guess as a TCS person, I'm much more comfortable making assumptions about or believing the hardness of problems about doing things with general purpose circuits. Mm-hmm. So something that people have been asking me about a little bit recently that I think I guess the community must have thought about this before. Maybe I've just missed it, but so one thing you can always do for a quantum advantage is you can take a random circuit subject to having a period in the sense of Simon's problem, right? And then you can output this circuit. And then ask if it's classically easy to find the period. Now you can specify whatever distribution you want. So one thing you can do is say take some sort of cryptographic obfuscator and run it on some very natural a circuit that's obviously has the period. The algorithm that says take your input, reduce mod some lattice, and then output a PRF or something like that. Seems very unlikely to me that a classical algorithm is going to be able to find the period on that distribution of explicit circuits. So it's like a white box versus black box difference in Simon's problem. That seems like a place where I'd be confident in the quantum advantage. And then the issue is, well, we don't have very efficient obfuscators maybe, and that's the problem. But, yeah, so just to completely ignore your question, that's another thing.
No, I mean, I would agree with the point that a fast classical algorithm for factoring seems more likely than a fast classical algorithm for everything that Shor's algorithm can do, right? For everything involving abelian groups, basically, right?
Cool. Awesome. Okay, so let's maybe go back to sort of the talks that you've taught us about, and maybe you can all sort of give us one important open question from maybe the field that you've been telling us about, or the specifics of your talk.
Well, it seems that the thing that I talked about has been broken already by Noah Shuddy. So I guess one open problem is there a way to fix it?
Okay, that's exciting.
Can you tell us more?
Yeah.
Well, I guess it's a bit technical, but I guess it uses this Aurora G linearization approach to solve systems of polynomial equations. In some sense, the idea here is that when you have this f of ax thing, you can pick random x's to evaluate this on, and then you can get as many equations as you like in the entries of the matrix A. Right. And then you do the Aurora G thing to try to recover A itself. So that's all she wrote. But maybe there's a way to fix it. Mm-hmm. But then, obviously the question is, there was kind of, I guess, the point of the talk and the point of what Scott has talked about before, which is, can we find something that is at the intersection of all those three areas? So it's quantum advantage, it's verifiable, and it's also implementable in the near term. Mm-hmm. So I guess right now, assuming this correlation thing doesn't work out, then in the horse race, it's back to like factoring and these types of things.
So, for example, like a concrete example of this, like peaked random circuit sampling, where you have a heavy output string that you can use for verification, would be one example.
Yeah. Nice. Do you have one, Andre?
So, well, coming from cryptography, maybe making cryptographers even more scared about quantum factoring. But then we've already moved on to post-quantum crypto. So actually, there's not much new here for cryptographers. But what I find really interesting is that in this room and among the people I've met this week, there are many people interested in proof of quantum advantage. And I'm practically sure we haven't reached the limits in terms of space and gate counts you can have on an actual crypto problem to solve with Shor's algorithm to get a proof of quantum advantage. So that would be an interesting open question to like push this further down in terms of costs.
How much room do you think there is to push it further down?
I don't want to make estimates because then Craig Guinea will do better. So
Good. Alex, do you have a?
Yeah, sure. So I just gave some open problems more directly related to my talk, but maybe more broadly, I think it would be good for the community to spend more time thinking about what pseudorandomness properties they actually want random circuits to have, like to come up with a more clearly defined heuristic of here are these kinds of properties, these types of properties are things we'd like to conjecture random circuits have. And that would then give the community more time to think about how true these things are. Yeah, develop a theory like we have for the random oracle heuristic classically.
Mm-hmm. Nice. Sean, you had another point.
Yeah, I mean, I don't want to make a claim that this is the big open problem in the field or anything, but something that I think maybe was tacit in my talk that maybe should be made explicit, and Daniel Greer and I were talking about this earlier, is that sort of the second result that I presented gives the prospect maybe of proving hardness of sampling even if you don't prove the permanent of Gaussian's conjecture. And whereas we've thought about PGC a lot and we recognize that it's difficult to solve, the techniques for that second method are pretty new. So it's possible that we could actually make much more progress on that problem and potentially show hardness of sampling even if we haven't proven PGC. Mm-hmm. So I think that's worth thinking about.
Nice. Okay, and if we flipped it around, if everybody, got to ask a question to someone else on the panel, like what question would they like to see answered? Maybe Scott can start, because he hasn't actually given a talk.
Yeah. So what other proposals like Andrew's that we heard this morning is anyone willing to stick their necks out and offer? I mean, I would like to encourage more of that, and all the more so if the proposals that we have are getting broken.
Mm-hmm. Nice. Anyone else?
I can maybe ask Andre. I guess we chatted a bit about this in one of the breaks, but I guess I'd be very curious how efficient you can make quantum algorithms for like breaking elliptic curve cryptography.
Yeah, I don't have very good prospects for this at the moment, but
Nice. Okay.
Yeah. Oh, I mean, I would really like to know whether there is a candidate hard instance of Simon's problem, mm-hmm. or let's say just a candidate hard instances even for the Shor period finding problem that look fundamentally different from the ones that we know.
Okay.
What qualifies as fundamentally different from the ones that we know? Sorry, it's just...
Okay. Here would be an example. Let's say not computable by a log depth circuit. I'm just giving one example of what would be.
Sure. Okay. So it's just the following answer is probably unsatisfactory, but in a recent paper with Rahul Alongo, we wrote down an explicit candidate which said if you have a classically secure indistinguishability obfuscator, which we have candidates for, then we can write down something which is hard provided that the white box version of Simon's problem is hard in the worst case.
Oh,
an
I
explicit-
see. Right.
yeah.
So you're saying if there is a secure instantiate, if there is a hard instance of Simon's problem, and if IO is
Yeah,
works,
basically that.
then your thing is a hard instance of Simon's problem.
Yes, but
Nice.
the
that is the kind of result that IO gives you, right?
yes.
Yeah.
But it's
Yes.
it's a little bit better than that because it just assumes that there's no worst case out there. That is as long as there's no way to generically on any circuit that has a period find the period, then you get a hard distribution. That's what's maybe slightly
Oh, neat. Send me that paper. I think I missed that. Yeah. Cool.
Awesome.
For depth, you can take these like nested pointer chases.
Yeah, but then will that also be a periodic function?
You want to like the whole nested thing.
Yeah. Like I want a function that is periodic, just like modular exponentiation, but that sort of has less structure than modular exponentiation. And of course, it's hard to formalize what I mean by that. But one example would be let's find something that's not in NC1.
Okay, so maybe we can, in light of the time, move on to thinking about experiments and sort of connections to experiments. And I think my first question to each of you is, what the next sort of big, so suppose quantum supremacy experiments have been done, what's sort of the next big TCS experiment you would like to run, and how big does your quantum computer have to be for it?
I mean, I don't have a good answer to this, but one thing I'll say is that there's one thing that I'm super curious about, which is when we actually have fault-tolerant programmable quantum computers, will it really be the case that just letting people write programs on these things will lead to many new discoveries of quantum algorithms? Because this has been an argument that people have made, that the reason why there's kind of this, like drought in coming up with new quantum algorithms is because we have to do things the old-fashioned way with like pen and paper. But that if we actually had a quantum computer and we could just like run experiments on it willy-nilly, then we would come up with like new and interesting algorithms. So I think like to me, like just having something like that and playing around with it would be super interesting to see if it leads to like new insights and new discoveries. But I can't name like, like one specific thing necessarily.
And how big does your quantum computer need to be?
I don't know, like let's say 1,000 logical qubits.
So, okay, good.
Yeah, I mean, this is not an answer to your question, but to sort of elaborate on this point. Escapes me. I'll come back.
Okay, great.
I'm interested in crypto. My guess is that crypto-related problems currently start at 500 qubits, logical qubits, and about 100, 500, I guess, and about 100 million to a billion Toffoli gates. I'm done. That's it. That's how big it needs to be. And since I'm only I mostly know about the crypto-related problems. I don't really know about what else you could do. So,
sort of, our obvious limitation, being inclined to theory as we are, is that of course we're trying to prove sort of speed ups or give some sort of kind of rigorous guarantees. Of course, that's not how a lot of useful classical computing goes, right? I mean, in principle, a lot of machine learning is sort of provably hard, but that doesn't seem to say much about the actual instances that we see, right? So maybe if you work on VQE, your dream is that it'll be like backpropagation was in the 70s. And until you have good hardware on which you can run these algorithms, there's not much to be said at the moment, or at least it seems like our theory tools are very limited. But you might hope that if and when we have hardware, you can just implement it and see how it performs. And then the theory to support it or lack thereof will be irrelevant. Mm-hmm. That might be one's hope. So that's just a way to sort of paraphrase this sort of point.
Yeah. I mean, it's now been a quarter century that we've had these heuristic quantum algorithms, like the adiabatic algorithm, quantum annealing, and so forth, that have been in this sort of limbo, right? Where, in principle, we now know that there is some black box solution landscape where they can find a global optimum exponentially faster than you could find one classically. But does that translate into sort of they're giving any speed up on a real problem that we would care about, let's say beyond the Grover speed up? I think that after all these years, that remains as big a question as it was when I first entered this field, and that is clearly one of the first things that we would try to address if we had, let's say, 1,000 logical qubits. Would be looking at different optimization problems, of course, doing the experiment very carefully, because experience has shown that people want to say that there's a quantum advantage, whether or not there is one. And so, doing a really careful comparison against, not against classical brute force, but against the best classical heuristics that are out there. And, and seeing, can we generalize? Are there features of the fitness landscape that seem to play to the adiabatic algorithm strengths? I think that there would be lots of empirical work that we could do in that world.
Mm-hmm.
All right. Well, I'm also a cryptographer, and the thing that I would like to see implemented is a quantum bit commitment. So, of course, you can cheat and just implement a classical bit commitment, but what I would like you to do is implement a quantum bit commitment that is fundamentally using entanglement and isn't just obviously a classical cryptographic object. That might be very hard and ambitious, and so I apologize if that's too much to ask for, but it'd be very cool if we could actually do it.
So, about how big does your quantum computer need to be?
Well, let's see. So, you can do quantum bit commitments using basically phase states where the phase is computed by some pretty simple function. So I don't know. I don't think it should be horrible, but I don't know. I don't know any numbers bigger than 7. So.
Cool. Okay, so I guess my experimentalist friends are telling me that maybe in 5 years they have 100 logical qubits, which seems to be really far away from what everybody wants to do. Do you see any hope of sort of finding something in that space, and where would you look? Would you sort of try and soften some theory requirements on what you've been thinking about, or would you look somewhere else? That's sort of the space that I'm interested in right now.
I mean, quantum simulation has always been the most forgiving territory to look for quantum speedups that would, that might matter to someone in real life. That's been true for 45 years. I think that's still true. I think with 100 logical qubits, you should be able to do, simulations of various condensed matter models, the Hubbard model, things like that. The way that I think about it is that there's sort of a bunch of layers, that are sometimes glommed together here, right? Like layer 1 would be just get a speed up for estimating any physical quantity, meaning not for a sampling task like, boson sampling or random circuit sampling, but for estimating a quantity, right? Do that better than you could do it classically. The next layer beyond that would be estimate a quantity better than classically that is interesting to the scientists in the relevant area, whether that's condensed matter or chemistry or maybe even quantum gravity, that tells them something that they were interested in, that they could is not just about quantum computation, but is of independent meaning for them. And then the layer beyond that would be to estimate a quantity that is relevant to the battery industry, the photovoltaics industry, something like that. So I would try to do them in that order. But I think with 100 logical qubits, that should certainly be enough to start tackling that at least that first benchmark.
And what about sort of more TCS experiments, quantum advantage, verifiable advantage, sort of what I've been expecting, I guess, people to say?
But it may actually be that a useful application comes in exactly the opposite direction. So of course, one way that we could imagine doing something useful is that we have some kind of goal, and then you try to develop some kind of quantum algorithm that solves that problem. But there's this essay from the former director of the IAS on the usefulness of useless knowledge, and it's sort of an essay in praise of theoretical research, which I don't need to pitch to you, but the idea is that it's sort of uncanny if you look at the history of mathematics, for example. It's ripe with these examples of ideas that were developed for their own sake with no application in mind, and many of them uncannily seem tailored to some kind of problem that we need later on. So, I don't want to belabor that analogy, but in a very, very small way at least, the fact that, for example, random circuit sampling seems to maybe have some kind of connections to cryptography, I think is a surprise, because that's not the basis on which it was developed or where it originated. So I think that this sort of starting with something that with a very narrow scope that we find interesting, and then later finding out that there's a web of connections between that and other things that we may find interesting for other reasons is I think maybe the more organic way, let's say, that we might actually find that quantum computing is useful for something other than the obvious things that we expect it should be useful for.
Other takers?
Yep.
Yeah, so I think all of these are far better answers than what I could think of. But one thing I'll say is that in regards to like verifiable quantum advantage, it feels like one problem when you're so limited with the number of qubits that you have, like say 100 qubits, is that we don't seem to have a lot of interesting applications that are very space efficient in terms of the number of qubits. So things where your problem instance is of size n, your classical hardness is maybe like 2 to the n, and where the quantum algorithm actually uses n qubits, like not even 2n qubits, like really n qubits, right? Because if you're on a level where you only have 100 logical qubits, and say your classical hardness is like 2 to the n over 2, and like, now that's 2 to the 50, then that's already classically doable. And this seems like, other than what Scott mentioned, which is simulation, I don't really know of a lot of cases where, these sorts of algorithms exist, where you have like this like really hard, classical runtime that's like exponential in n, and where the quantum algorithm, doesn't really use a lot of ancillas or additional space. And this seems to be the challenge with verifiable quantum advantages. How do you achieve something like this? Like, is it maybe that the structure that you need to add to make it verifiable fundamentally requires you to use additional space or something along these lines?
I mean, let's very clearly pose this question. Are there number theoretic interactive protocols, for example, where you can get a quantum advantage using 100 logical qubits? Not 500, but 100. Right? I think there are people in this room who are much better placed to work on that problem than I am, and I hope that we see progress on it.
Wonderful. Yeah, maybe we can open up to the audience if they have any questions. You guys. Maybe I can.
I guess it's a two-sided question, and I talked to some people about it, but so it's about what is like near-term feasible in quantum computing. So we kind of intuitively understand that QKD is already like feasible, maybe on short distances, because it operates on single qubits. There is kind of no storage requirements and so on. Maybe recorrection is infeasible. It also, we see it in papers, people say, oh, unlike, BB84 algorithm, this one maybe has 2 rounds, but it's not here implementable in the near future. But I haven't seen like a formal definition of a model, complexity model, which will satisfy, me, Scott maybe, or whatever, other people, which will separate what is, feasible in the near future. Maybe there's 1 qubit operation, things which don't require a correction, from the theoretical results, because in theory we know that there is quantum advantage under like well-established assumptions and so on. There are all those papers about certifiable randomness and so on. It's just so to me it would be very interesting to define this near term model, like 1 qubit. What is this as a complexity model? And 2, if this model can be defined, do we actually have theoretical results of quantum advantage in this model? And if not, why not, right? Because to me that would be exactly what separates real world from theory, because in real world everybody thinks we can do QKDs. That's a practical problem. And here I talk to people say, oh, QKD, it's like, oh, I don't work on QKD, it's kind of uninteresting. I work on this kind of stratospheric, amazing quantum money and things like that. So to me, that would be really interesting to define this model of kind of QKD compatible things and see if we can probably have quantum advantage in this model.
But okay, what might complicate an answer to your question, if I understood it, is just to be clear, there are these sort of two different regimes when we're talking about quantum advantage. So, for example, my talk was entirely about the asymptotic limit. So in particular, we're not concerned with experimental particularities like noise, uncorrected noise. And then there is this different regime where you actually implement an experiment. So everything is a constant, everything is finite size. And you have a different set of concerns. And right, even the metrics for whether or not you've succeeded are completely different. So it doesn't make sense to ask, is there sort of an asymptotic advantage? Because you just ran a particular concrete experiment. You can ask, is there a wall clock speed up relative to the best known tensor network methods, let's say, or classical simulation algorithms? But that's a different question. And
I'm
so,
interested in the first one. I mean, both are interesting. Eventually, I'm interested in the first one because I think, sure, maybe initial asymptotics will not make sense or whatever. But to me, it will be conceptually very interesting to kind of say, okay, this is like QKD compatible algorithms, whatever it means, not a correction, I don't know exactly, and then build complexity theory, And if, for example, the answer is there is a fundamental reason that quantum advantage cannot be in this model, I think that would be something interesting. Conversely, if there is, a theoretical thing that may be asymptotically infeasible, that's yet another new avenue to demonstrate quantum advantage. But I haven't seen it, and I would be very interested to see this formal model or possibly models.
Any other questions from the audience?
So, Evgeny, basically what you want is a formal model of that which is not captured by formal models?
No, it's something where QKD would be in that model. It will be in this model, right? So we have a BB84, right? That's like practically feasible. Companies build it. So for companies, many people in the real world, they heard about QKD. They say it already exists, but they don't know about quantum money and all those amazing other things. So to kind of bring this practical, but define a formal model which includes
I mean we have quantum communication, we have certainly there is a formal model in which you can situate QKD and quantum money. It's basically the Alice and Bob model, say what kind of communication channel you have, what kind of information theoretic task you're interested in, how many rounds of communication you're allowed, and then this is a model where we've been studying quantum versus classical separations for decades.
So do we have a quantum advantage for provable quantum?
Yes, I mean QKD is one example. Quantum money is another. I mean, these both achieve tasks where you can wonder how useful it is. That's a question. But in any case, these tasks are just provably impossible using classical information.
Right. No, but QKD is not an example because we know how to do QKD based on RSA or whatever, something.
Yes. Information theoretically.
But that we cannot demonstrate information. Like quantum advantage means like polynomial.
Quantum. Right? I mean, you could say that quantum money is a more convincing example than by that light, because quantum money. I mean, if you want static information that represents your money, then and not have some intermediating third party, or let's say blockchain or something like that, then classically that's just not possible even with computational hardness assumptions.
But I thought quantum money is a stratospheric thing.
What?
I saw that according to my intuitive understanding, which quantum money, so QKD is here, quantum money is like, quantum money would be outside of my model.
I mean, the one thing that's harder about quantum money is that it seems to require, maintaining a quantum state for
Exactly.
a long
So I want to
period of
separate
time.
it. I want to exactly separate
Okay,
it.
maybe we can.
Public key quantum money. Scott, you're talking about private.
Oh, I see. So maybe, yeah, I see.
Well,
Yeah,
no, I mean, I'm talking about both, but as far as I know, like any quantum money scheme requires keeping a quantum state coherent for.
because that would be outside of my model. Yeah.
Public key quantum money scheme would not be like none of the candidates we have are near term, right? Like
No, they're not. They're certainly not near term. So I wasn't saying that. I was saying, classically, they achieve a task that is not possible even if we make computational hardness assumptions. That's the point.
All right. So maybe to finish off you have one more question? Yeah, please.
What is the scope of?
Sorry, can you use this?
Thank you. What is the scope of hybrid quantum architectures, like combining classical computation with quantum servers? Is there any practical implementation of it?
I mean, I would say that every quantum algorithm in practice is a hybrid algorithm, right? The control flow is being done by a classical computer. You might as well use the classical computer for everything that it can do and just use the quantum part for whatever it has to do. So I would say that is all quantum algorithms.
Thank you.
Yeah.
I guess there are also these approaches that like IBM specifically works on, where you try to combine quantum computing with classical supercomputing to try to solve some chemistry problems. So for instance, you have like some Hamiltonian for which you want to find its ground state, and you can try to initialize a quantum system that tries to sample from the spectrum of the Hamiltonian or something like that, and then like whatever samples you get, you then try to classically diagonalize the Hamiltonian using like supercomputing power with respect to the samples that you got. So you're kind of using quantum as something to like kind of boost the existing methods that we have to solve quantum chemistry problems.
One last question, and then we go to.
just to follow up to what Andrew just said, I'm curious, is IBM willing to mention some of the problem instances in this category that they're most interested in?
I mean, I don't know too much about this because I don't work on this. I think there are some papers already out on this by like Antonio Mezzacapo and others. But I know that they're interested in, like actually just recovering the ground states for like some very small molecules for which this hasn't been achieved classically yet, like using classical methods. And I don't know how large the molecules are currently for which this has been done, but I know that, they're trying to do like, the smallest molecule for which this hasn't been done yet classically.
So just if I understood you correctly, the idea is just the quantum computer is useful for data generation, and then essentially you do classical computing on that.
Yes, that's right.
Cool. All right, so maybe we can finish off by, I'd like to ask each of you to sort of pitch to the audience like a maybe big open question that you would like them to work on, and sort of pitch why you think it's an interesting question, or like why it's an important question, maybe what the obstacle is.
What's the scope here?
I guess in the context of quantum advantage, like in the context of, the types of things we've heard today, the types of things we've discussed in the panel. I think we're good.
Okay, I'll take an easy answer, which is information theoretic verification of BQP, like giving a protocol that can verify any problem that you can solve in polynomial time on a quantum computer, and do this verification without any computational assumptions, and so that the prover, the quantum computer, only needs to perform quantum polynomial time computations to convince you of this. So I guess, the motivation for this, there was this really nice paper by Umesh and Dorit Aharonov asking, is quantum mechanics falsifiable? And, this would probably be our best bet towards answering that question, because it would be like some sort of interactive experiment to test quantum mechanics itself. And the fact that it doesn't rely on computational assumptions means that, like you're absolutely sure about the result that you're getting. Like you don't have to assume anything. It's simply true or false, like what you're getting out of it.
Great.
And you don't want to use non-locality either.
Yeah, you don't want to use non-locality ideally. Yeah, I guess in that setting we know how to do it. Yeah.
Yeah, maybe this is just a specific example of that, but in particular, a quantum advantage scheme with efficient classical verification. Right? I think this is the big open question. Of course, based on my talk, I'm partial to things like the permanent de Gaussian's conjecture, but I think this verification thing is really perhaps the most important, at least for a quantum advantage.
Having some kind of proof of advantage based on a crypto problem which would not be factoring and which be much more efficient. So this is related to what we've seen today. And this could be Yamakaiwa's Andre, this could be anything. This could be Simon's algorithm and then some clever tricks. I don't know, which is why it's an open question, of course. That would be super interesting, actually.
I mean, I've been flogging this horse of verifiable quantum advantage for years, so I'm not going to have anything to say that's terribly new here. But since it only briefly came up today, let me mention again the question, is there an efficient classical algorithm to distinguish a random quantum circuit from a random peaked quantum circuit? Okay, and relatedly, is there a fast classical algorithm to generate a random peaked quantum circuit? If the answer to the first question was no, and the answer to the second question was yes, then that would be our verifiable NIST quantum advantage proposal right there. We'd be done. So I think it would be interesting to know.
It's a constant depth.
Oh yeah. I mean polynomial depth. Yeah, good.
All right, so I'll take a somewhat different track than some of these answers, but I'd really like to understand, like, what is the smallest classical computational hardness assumption that you need to make for there to be like a non-interactive proof of quantumness? So let's say that I let you assume any quantum hardness assumption that you want, for example. Yeah, any hardness assumption which is not about classical computers not being able to solve problems that quantum computers can, assume whatever you like. Then can you demonstrate quantum advantage which just relies on the assumption that BQP is hard for classical algorithms or something like that? It's I don't think it would be crazy to be able to prove something like that. So yeah.
Factoring you don't like, or factoring?
Yeah, no, I do not like assuming that. Yeah.
Because it's too strong? Or?
Yeah.
Awesome. Cool. So with that, maybe we can conclude the panel. Thanks all for sticking up. Thanks all for the great discussion. Thank you.